Every time you compile a Java program, your human-readable syntax is stripped away, converted into a dense stream of binary instructions known as bytecode. For many developers, the journey stops there. They feed that bytecode into the Java virtual machine, treating the JVM as a black box that executes the logic. Looking at this architectural diagram, the JVM operates as a three-stage processing pipeline, consisting of the class loader, the runtime data areas, and the execution engine. This pipeline pulls in your code dynamically, manages memory autonomously, and compiles machine instructions on the fly. Tracking a single file of bytecode through these three stages reveals exactly how Java manages memory allocation and CPU cycles. This mechanical understanding is the key to debugging memory leaks and writing highly optimized software. The life cycle of our bytecode begins the moment a Java program is invoked. The compiled files sit on the disk, waiting to be executed. They must first pass through the class loader. It functions as an intake manifold, preparing external class files for active memory. However, it operates on lazy loading, only pulling a class into memory when explicitly required. Loading thousands of classes simultaneously would saturate the system's RAM immediately. Deferring that process keeps the application's initial memory footprint strictly contained. The class loader functions as an efficiency-first gatekeeper, preventing memory saturation by strictly controlling the flow of data before execution begins. Once inside, bytecode enters the runtime data areas, strictly partitioned into shared and thread-isolated memory. In shared memory, the class area receives the bytecode, storing structural metadata and blueprints. Adjacent is the heap, the JVM's massive primary workspace. The heap is where all actual objects live. Using the new keyword spawns a dynamically instantiated object directly into this shared expanse. Because it is globally accessible, this space fills up quickly. To prevent overflowing, the JVM runs an autonomous background process called the garbage collector. The garbage collector constantly scans the heap. When it identifies an object no longer reachable by your program, it reclaims that memory to be reused. The shared memory space acts as the global state, a heavily trafficked area relying entirely on garbage collection to prevent terminal memory exhaustion. Crossing into the restricted thread-isolated memory, we see distinct lanes for concurrent threads. Each active thread gets a private thread stack. Invoking a method pushes a new stack frame block onto the stack. When finished, that frame is instantly popped off and destroyed. If a second thread is running simultaneously, it has a completely separate, inaccessible stack of its own. Data cannot leak between them. To manage frames, each thread gets a dedicated tracker called the PC register. As the stack grows and shrinks, it points to the precise line of bytecode currently executed by that thread. One final component in this isolated zone is the native method stack, running alongside standard Java stacks. Java often needs to interact directly with the operating system or execute C++ functions. When the Java native interface makes those calls, execution data is stored here in the native method stack. By physically isolating stacks and registers per thread, the JVM natively guarantees thread safety for local variables. This bypasses the need for complex manual state locking mechanisms. The blueprints are stored, variables isolated, and objects staged. Now, the bytecode must actually be translated into physical CPU instructions. In the execution engine, we see a dual-path architecture, the interpreter and the just-in-time compiler. The default interpreter path reads bytecode strictly line by line, converting and executing one instruction at a time. This creates a bottleneck. The interpreter repeatedly retranslates looped bytecode. To solve this, the just-in-time compiler monitors the application, intercepts frequently repeated hot methods, and transforms the entire repetitive block into one optimized chunk of machine code. Next time the program calls that method, it executes raw machine code directly, eliminating translation overhead and pushing Java speeds near compiled languages like C++. The execution engine is an adaptive system, intentionally balancing the quick startup of an interpreter with the long-term performance gains of a compiler. Pulling back to the complete architectural diagram, we can see how these subsystems function synchronously as a unified pipeline. Lazy loading pulls the file, the class area stores the structural blueprint, and the heap allocates the volatile object. Thread-isolated stacks frame the local variables, while the JIT compiler accelerates the hot paths. The entire system hinges on the separation of globally shared, garbage-collected data from strictly isolated execution contexts. Adopting this mental model changes how you write software. You stop treating the runtime environment as a mystery and start designing code that natively respects these specific memory boundaries. Java handles the heavy lifting of memory management and machine translation for you. But mastering this internal pipeline is the final step in architecting truly high-performance systems.